Let's talk about heaps. We talked about heaps previously. Let me just recap a heap. So here's a heap. Let's say we have a 22. We have a 17. We have a 19, 11, a 7, a 12, a 15, a 6, a 9, a 10, and a 5. Is this a min heap or a max heap? It's a max heap, absolutely. The largest numbers are at the top, okay? And remember when we talked about traversals, traversing through trees, we talked about 4 different ways that you can do traversals. We talked about in-order traversals, so we do left, root, right. We talked about pre-order traversals, where we go root, left, right. And we talked about post-order traversals, where we do left, right, root. And we also, the 4th way we talked about was a level order traversal. And I want to number these nodes as if we would visit them in a level order traversal. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so 10 nodes. So if we look at these nodes, there's a relationship between the children and the parents. Okay, if we take a node, for example, node 3, its children are 7 and 8. So the children are 2 times the parent, 3 times 2 is 6, plus 1, or 2 times the parent, plus 2. Okay? That's true for all the nodes. The root node is node 0. Its 2 children are 1 and 2. 2 times 0 plus 1, 2 times 0 plus 2. Node 2, its 2 children are 5, 2 times 2 plus 1, and 6, 2 times 2 plus 2. So for every node in the tree, that relationship holds. That relationship's only good for a 0-indexed relationship. If you have node 0 at the top, if you have node 1, then it's twice the parent and twice the parent plus 1. But have a 0-indexed relationship. Let me write that down here. So children are 2 times the parent plus 1, 2 times the parent plus 2. And so we can also, of course, go from one of the children back up to its parents. Okay? And so the parent is the floor of the child minus 1 divided by 2. This node we would visit in the 10th node in a level order traversal. 10 minus 1 is 9, divided by 2 is 4.5. The floor of 4.5 is 4. 9 minus 1 is 8, divided by 2 is 4. 8 minus 1 divided by 2 is 3.5, and so on, okay? So for every node, we can either figure out what its 2 children are or what its parent are. So the parent is the floor of child minus 1 divided by 2, okay? And so if we want to code a binary heap, one of the ways that we can do that very easily is to just use an array and use this relationship. Start filling our array at position 0, 1, 2, 3, 4, 5, and we'll keep going, right? So we keep filling our array basically using a level order traversal. So let's take a look at the code for coding a binary heap. So in our binary heap class, we'll probably have a couple of globally scoped variables. We're going to have something called last position. And last position is how far along we are in our heap, okay? So how many elements we have basically in our array. So typically what we would do is we would make an array much larger than the number of things we want to put in it. And then last position will just keep track of where we've added stuff. And you'll see why we use that in a second. And then we're going to have a globally scoped generic array. I'm going to call that array. And of course, the way we do that is we just make a new array of objects of whatever size we want. Okay. So these definitions are going to be in our constructor. They're going to be globally scoped variables that we're going to access. Okay. I'm just not putting all of that code up there. Now remember our code for adding something. When we want to add something to our heap, how do we do that? We put the thing that we're going to add in the next available space. In this case, it will be the left child of the 11. And if we're adding something, say we're adding the 25, we put it in the next available space and we compare it to its parent and we say, is it bigger than its parent? If it's bigger, we swap them. So we put the 11, we swap that with the 25. And now we say, is the 25 bigger than its parent? If the 25 is bigger than its parent, we swap them. If the 25 is bigger than its parent, we swap them. Okay? So this is our TrickleUp maneuver. So for our add, we're going to have a recursive TrickleUp. We're going to add something in the last available space, and that's defined by last position. And then we just compare it to its parent. We know how to get the parent from a position, right? And we go up either until it's less than its parent, in which case we don't do any more swaps, or until we're at the root position, in which case we're done. So, for example, for our add method, we're going to have, let's say, a void add, and we're going to take an E object to add. And we're going to put that thing in the last position in the array. So last position right now currently holds the index of the last thing in the array. So what we want to do is increment last position and then use that. And so we're going to say array plus plus last position equals object. And notice the difference. This time we're using plus plus last position, which means we increment the last position counter and then we add our thing there. Okay. And then we're going to call TrickleUp. And TrickleUp is going to take the position of the thing that we've added. It's going to figure out what the parent is. It's going to say, are you bigger than the parent or smaller than the parent? And if you're bigger, we're going to swap you. There's lots of different ways you can do the swap. And I recommend you just do a very simple algorithm where you take two integers, let's call them from and to. We create a temporary variable for the first element. Then we overwrite that element with the thing we're trying to swap. And now we set the thing that we've just swapped to our temporary variable, and we're done. Okay? It's a simple algorithm. It works every time. There's other ways you can do it, but this way is guaranteed to work, and I highly recommend you do that. So we've got our swap method, we've got our add, we've got to figure out what our trickle up is going to do. So remember our trickle up, what we're going to do is we're going to compare our item to our parent, and if we're bigger than our parent, we're going to swap, and we're going to keep doing that until we get to the root. So our stopping conditions are either we're not bigger than our parent. If we're smaller than our parent, we don't do anything, or we're at the root position. And we know we're at the root position because our current position would be 0, right? So our trickle up method is going to take a position in the array that we want to trickle up from. Initially, that's last position, that's where we've added things, but it will go up the array as necessary. If we're at the root position, we're done. So if position is 0, we're done. We don't need to do anything. Let's get out of there. Okay. If we're not at the root position, we need to find our parent. So we subtract 1 from position and divide it by 2. That's how we find our parent when we take the floor of that. And then we say if the array at parent is smaller than our current position, or if our current position is larger, it doesn't matter which way around you say that. So let's say if array, actually, let's use generics to do this comparison. If comparable E array position dot compare to, I'm going to have to carry on down on this next line, compare to array dot parent. So if position, that's where we are, is larger than our parent, so our comparison will return greater than 0, then we're going to swap position and parent, and then we're going to do a trickle up on parent. So we look and see, is the thing we've added larger than its parent? If it is, we swap them, and then we go up to that node and say, is that larger than its parent? And if it is, we swap that. And then we go up to its parent, is that larger? Until we either get to the root or until we get to some position where we don't have to trickle up any further.